Next, we will look at a simple way to determine the acidity or basicity of a solution. In other words, how acidic or basic is it? And our measure of this is the pH, which is just equal to the negative log of our concentration of H3O+. The P will always mean negative log in this unit, and that negative sign causes there to be an inverse relationship between concentration of H3O+ and pH. So that if we have a lower pH, that means we must have a larger H3O+ concentration, which in turn means it's more acidic. And then, of course, we can say the opposite. A higher pH means smaller H3O+ concentration, less acidic, or more basic. And so keeping our temperature at 25 degrees Celsius, we could use the concepts in the last video to quickly prove that if the pH is equal to 7, that's what we would get if our concentration was 1.0 times 10 to the minus 7, which is what we have in pure neutral water. So at pH equals 7, we have neutral. And so if our pH is less than 7, that means our pH is going down and our H3O+ is going up, so we would no longer be neutral, we would be acidic. And the lower it is, the more acidic the solution. And in turn, if the pH is above 7, then we're basic. And so, for example, if we had a concentration of 5.8 times 10 to the minus 6 molar, so this will be our concentration of H3O+, and we took the negative log of that value, we would get 5.24. And there are no units after you do a log. The units go away, so pH is unitless. Now you might think that I just made a mistake with the significant figures. After all, this number here is 1, 2 sig figs. This number here looks like it's 3, because when you take a logarithm, any numbers to the left of a decimal point of the resulting answer are not factored into significant figure considerations, because this number here, without going too deep into the math of it, relates to this number here, the order of magnitude, which we also don't take into consideration with sig figs, because it's an exact number. So only numbers to the right of the decimal are significant. Let's write that down. We'll star this note after log. Only numbers to the right of a decimal, only numbers to the right of decimal are significant. And so this number here really is only 1, 2 sig figs. And I will include a slide at the end of the posted PowerPoint slides that helps try to explain this math a little bit better for those who are bothered by this. But it's not important that you understand the math. In this class, it's enough for you to just know that after you take a log, only numbers to the right of the decimal are significant. And so I'll just add one more note, which is how to go backwards from a pH value to the concentration of H3O+. And that's just going to be equal to 10 to the minus whatever the pH is. Any questions? This really is simulating the classroom environment. And so this right here is a nice figure describing the pH of various substances that we might find in life. And also note at the bottom, there are other types of p-values we'll be seeing in this unit, like pOH, pKa, pKw, and that just means negative log of whatever that term next to the p is. pKw, this is a relationship that's important for later, but we'll bring it back when it becomes important. Now we'll end this lecture with a brief overview of some very important terms that will just be hammered in as we do examples, and thus it's slide reliant. I would not recommend writing anything down unless I tell you to. So on this slide, we'll cover the definitions of strong and weak acids. Strong acids ionize 100% in solution. The reaction effectively goes to completion, and so we just use the forward arrow. And so this HA is a generic way of representing an acid. It's just a proton and everything else that will be left behind after reaction. This is what the conjugate base winds up being. So any strong acid, notice the list over here, any strong acid will always just react with water and lose that proton completely to the water. And to use the simpler shorthand, we don't bother writing the H2O, we just say HA 100% dissociates into protons and A-, which is what's pictured here. In other words, a strong acid is a strong electrolyte. It's just a specific type of strong electrolyte that breaks into protons and the anion that's left over. And let's just emphasize one more time, these protons will not remain protons swimming in water. They will all find an H2O and form hydronium ion. Now over here we have carbonic acid, which is a weak acid. It's a weak electrolyte. It goes into water and partially dissociates into H+ and the HCO3- anion, but then these start reacting together to reform H2CO3, and so we never fully dissociate all of the different carbonic acid molecules in that water. So weak acids partially ionize. They form an equilibrium, which is what was just described. And if there's an equilibrium, there must be an equilibrium constant. And we give that constant a special subscript A. We call it the acid dissociation constant. But just like previous Ks we've seen, the subscript doesn't change the rules. It just tells us what type of equilibrium we're dealing with. The A tells us we're dealing with some acid dissociating into protons and anions. And they will always react in the same manner no matter what the acid's identity is. And so Kas always wind up looking like this. For the products, we will always have protons and the leftover anion. And for the reactants, we will always just have whatever concentration of weak acid is left over after equilibrium is achieved. And we'll see this so many times that it's not worth writing this down right now. It'll just be hammered in by application. What is worth writing down is this note in the bottom right corner. Must know all strong acids. These are the 6 that you are expected to be familiar with on exams. And we also have strong and weak bases, which have very similar definitions. A strong base is a base that ionizes 100% in solution. The reaction goes to completion. The classic would be NaOH. Dissociates totally into Na+ and hydroxide. You're also expected to memorize all the strong bases, but this is a lot easier to do because we're only going to memorize these first 5. And if you look at a periodic table, you'll see that they're all group 1 elements paired with a hydroxide. A weak base only partially reacts with water. The base will accept a proton from the water, forming BH+, a conjugate acid, and leaving behind hydroxide. But then these two will start to react together to reform our weak base, and so an equilibrium is reached. And that equilibrium has a K value associated with it, and we give it a subscript B for base. One more point worth noting, unlike a strong base, which clearly breaks apart and produces a hydroxide ion, the weak base does not produce a hydroxide ion. Look at the classic weak base ammonia. Where does the hydroxide come from this molecule? It has no hydroxide to give. The hydroxide results from the NH3 taking the proton from water, which in turn causes the water to leave behind the hydroxide. So weak bases that we'll see produce hydroxide in this manner. It's not as direct. So that's the lecture. Lots of information. Most of it we'll learn by just application, which we'll get into next lecture.